X-rays. In this video, we are going to explain the origin of X-rays, how they are pictured in current times, the repercussions in medicine, and the effects of high-dose radiation in patients, among other things. Electromagnetic radiation include from radio waves to X-rays, passing through microwaves, infrared radiation, visible light, and ultraviolet radiation. X-rays are the most energetic range of the electromagnetic spectrum. X-rays are a form of electromagnetic radiation, similar to visible light. Unlike light, however, X-rays have a higher energy and can pass through most objects, including the body. The X-rays, gamma rays, radio waves, heat, and light are waves of electromagnetic radiation that have the same nature, have no mass or charge, and travel at the same speed of light, where the difference is its origin and its wavelength. X-rays originate in the electronic orbits where electrons are. X-ray tubes are without air, consists of two parts. Cathode are tungsten filaments, anode is a plate which turns them into photons to prevent wear and tear it spin that electrons do not strike at the same point, maybe tungsten bonds, molybdenum, mammography. Compton dispersion and photoelectric effect. X-ray, as other radiation, beams suffer scattering or Compton dispersion. That is a general physical process where some particles are forced to deviate from a straight trajectory. Collimators are used to avoid scattering. Photoelectric effect is the absorption and transmission of photons, which is different depending each object. To create a radiography, a patient is positioned so that the part of the body being imaged is located between an X-ray source and an X-ray detector. When the machine is turned on, X-rays travel through the body and are absorbed in different amounts by different tissues, depending on the radiological density of the tissues they pass through. Radiological density is determined by both the density and atomic number of the materials being imaged. For example, a structure such as bone contains calcium, which has a higher atomic number than most tissues. Because of this property, bones readily absorb X-rays and thus produce high contrast on the X-ray detector. As a result, bone structures appear whiter than other tissues against the black background of a radiography. Conversely, X-rays travel more easily through less radiologically dense tissues such as fat and muscle, as well as through air-filled cavities such as the lungs. These structures are displayed in shades of gray on a radiography. Contrast limit. Plate radiography. It was the first visualization method of X-rays that used silver plate to reveal the image, actually are replaced by digital radiography. However, in some places like hospitals, these plates are used. For the computer radiography, the plate is made of reusable phosphorus. In this radiography, the spatial resolution is worse than plate radiography. In the digital radiography, there are no more plates. The image is displayed by the action of semiconductor sensors. The fluoroscopy is a technique based in the multiplied photon that intensify the visualization of the image. This means the temporal resolution is much better. For example, in radiography, you can appreciate the fluid blood movement. Risks. X-rays also produce ionizing radiation, which is a form of radiation that has the potential to harm living tissue. This is a risk that increases with the amount of cumulative lifetime exposure. A small increase in the possibility that a person exposed to X-rays will develop cancer later in life. The possibility of cataracts and skin burns, but only at extremely high levels of radiation exposure. Current research of X-ray technology focuses on ways to reduce radiation dose, improve image resolution, and enhance contrast, materials, and methods.